Welcome to this video on the derivation of the sine rule. On the right hand side of the page here, I have the trigonometric identities for right-angled trigonometry. And down below, I've got these two extra rules called the sine rule. In this particular video, I'm going to show you how I use these right-angled trigonometric ratios to derive the sine rule here, which we use in non-right-angled triangles. Now, to jump straight into it, consider I have a non-right-angled triangle, as shown here, and as you can see, because there's no right angle, I can't use these regular trigonometric identities here. But what I can do is I can partition this non-right angled triangle such that it becomes two smaller right angled triangles. So I'm going to draw a red line down the very center, starting from one of the angles down to the base of the triangle, and then I'm going to make it such that it touches or interacts with the base of the triangle at 90-degree angles. Now, to further annotate, I'm going to call the angle on the left hand side alpha and the angle on the right hand side beta. And notice that this red line in the center, that's going to form the side of the opposite. And we know it's the opposite because looking at angle alpha, it is opposite the angle, and looking at beta, it is also opposite the angle beta. Now, the other two sides I'm going to use to prove to derive the sine rule is I'm going to say that on the triangle with alpha in it, we're going to label the hypotenuse, and I'll call that H alpha. And on the other triangle containing beta, I'm going to find the hypotenuse there and call it H beta. Now, what I'm going to do is I'm going to use the sine ratio, so sine theta equals opposite over hypotenuse, and derive both of those equations for the triangle containing alpha and the triangle containing beta. So what that is going to look like is sine theta equals the hypotenuse underneath the opposite, or opposite over the hypotenuse. Then substituting in the values, we're going to get sine alpha equals the opposite over the hypotenuse alpha, and then rearranging to make the opposite the subject, we will get opposite equals hypotenuse alpha times sine alpha. Now this is, let's call it our first equation, and our second equation, if I follow the exact same rules to the triangle containing beta, notice that it is the angles, they look to be different, but it's just a mirror image with slightly different side lengths and different angles. So the ratio itself will still be the exact form as what I did with alpha. So therefore we can say that the opposite in terms of beta is going to be the hypotenuse of beta times the sine of beta. Now, bringing it all together, I'm going to equate equation 1 and 2 because they are both equal to the opposite, which is this red line down the middle here. So acquainting both of our mathematical models, we've got the hypotenuse alpha times sine of alpha equals the hypotenuse of beta times sine of beta. Then rearranging, what we're going to get is the sine of alpha over the hypotenuse of beta, then the sine of beta over the hypotenuse of alpha. Now, as you may have identified, when I was annotating this triangle, I did not use the naming conventions that we use in non-right-angled trigonometry. Now, if I go back in and we say, rather than using the Greek letters here and the hypotenuse, what if we use the Roman alphabet, and rather than alpha, we have angle A rather than beta, we have angle B. And I didn't name this angle up here, but just for convention's sake, let's just call it C. Now we know that we always call the sides opposite the angles by their lowercase. So notice that for angle A, the opposite side is going to be over here, and we will call it little a. And little a corresponds to the hypotenuse of beta. Now going over again, angle beta is opposite what was the hypotenuse of alpha. We're going to call this little b. And finally, just for complete sake, we will name the side opposite angle C little c. So what we've done in green is all of our sides and our angles have been named using the non-right angled naming convention. So if I go back over, and I'll actually write it in green pen to make it more apparent. If I rename, or if I change the names from the original convention I used and use the proper non-right angled naming convention, what we're going to get is sine A over A is equal to sine B over B. And I know I didn't derive it, but imagine, or suppose that if sine A over A is equal to sine B over B, if we did the exact same operations but slice the triangle in a different way, what we'd find is we could acquaint sine A over C to be the same as sine C over C is equal to sine B over B. So just for completeness sake, this would also equal sine C over C. So what we can see in the yellow here is this is a derivation of the form seen over here in the yellow. Now some of you may be asking, how do you get to the same form in the color of teal? Well, by simply inverting or taking the reciprocal of both sides. So if we've got, say, sine A over A equals sine B over B, if we want, we could simply raise both sides to the -1. And we know using our index laws, anything raised to the power of -1 flips the fraction on the inside. So therefore we get A over sine of A is equal to B over sine of B. So there we have it. We have proven, by using the simple operations of partitioning our non-right angled triangles such that we have two smaller right angled triangles, we can derive the sine rule in both its form where the sine of the angle is over the side and the side, and similarly the side over here is over the sine of the angle, thus proving the sine rule.